up here.
All right, how's everyone doing?
Okay, first this is where while loops are getting you.
Any issues with the worksheets? All right, go ahead and pass those in just so I can look at them, see how people are doing. Yeah. That's fine. Yeah, that'll work. Like I say, I'm not grading them. I just want to sort of see if it's making sense to people.
Right here.
Yeah, thanks.
Here you go.
All right, any problems with ODP 202?
Wait, am I working on 2 or 203?
203 is today's. Yeah, that's fine. Thanks. All right, so let me just show you my code for ODP 202. Pretty straightforward. So you have to define what a struct node is in any file that you're going to use struct node. Okay, ultimately things get linked together, but when you're compiling, even though the main program knows what a struct node is, GCC doesn't understand a struct node unless you tell it what it is.
Is it preferred to have it as a global variable?
Have a what?
As like a global variable?
So it's not really a variable, it's really a declaration of a data type basically, and that's best in the beginning of your file outside of all your functions.
Kind of like define statements and stuff like that?
Yeah, basically. And you should be able to define it inside a function, but you'd need to define it inside every function you use, and typically we just put it in the very beginning, and more typically, eventually we will actually make a separate file, like pa1.h, that'll include those statements for a struct node, and then we'll just include pa1.h in the top of every file. And that's a lot of what in stdio.h is a bunch of structure definitions. So yeah, put that in the very beginning. You do not need a typedef statement, but if you like typedefs, typedef lets you basically say, in this case, whenever I say uppercase node, what I mean is lowercase struct node. And anywhere that I want to use a struct node, I can either say struct node or I can just say uppercase node. And if I want to pointer to a struct node, I can say just uppercase node with an asterisk. Okay, so it's a nicety, but it's not essential. So this could just be struct node star. All right, and then the init function, it returns void, so there's no return value. Yeah?
How is typedef different from pound define?
Oh, that's a good question. You know, pound define struct node would basically do the same thing. I don't know. Pound defines are a little heavier handed. They're really kind of, because pound defines get resolved before any actual compilation takes place. There's something called a preprocessor, CPP, that runs through your file and replaces all the pound defined things with what they're equivalent to.
And what does the typedef do?
And a typedef is ingested by the compiler itself. I don't know if there's another difference. I can almost guarantee if you look on Stack Overflow, there's some like really violent discussions about it though, about why one would be good and the other would be like, you know, horrible. But I don't know actually. I've never really thought about that. But it's pretty typical to use a typedef. Okay, that's probably the more preferred way to do it. But I can't think of why a define would do anything different in the end. All right, so init, it's type void, so it doesn't return anything. It takes one argument, which I'm calling LL. You can call it anything you want, but it does have to have a name. If I just say struct node star parenthesis, it's like saying, you know, integer sum parentheses int, right? When you have an argument to a function, you've got to say what type of argument that is, but you've also got to have a name for that argument so that you can access it. So here I'm saying struct node star LL. So LL is the name of my array. So this was the code that we wrote out yesterday to initialize the Sentinel node. So LL 0.data is 42, .next is -1, .valid is 1. And then here's the for loop that basically goes through the other 99 elements. So 1 through 99 inclusive, sets data to 999 next to that and valid to 0. And then I could just say return, or I can just fall off the curly bracket and I'll return automatically. So that's a fine init.c. All right. As of this morning, a total of 6 people had created a repository for linked list 1 and added me as a reporter. And a grand total of 2 people had emailed me and said, can you check to see if you have access to my GitLab repository? All right. And I mentioned in the beginning of the week, if you do this week and you send me an email and say, can you make sure that I've done this right, I will be happy to check and send you an email back and say, yes, you're good, or no, you know, try doing this and that kind of thing. Tomorrow's your last day to do that. Okay, if you don't do that by tomorrow, you're taking a chance that you know how to set this up and nothing's going to go wrong, and you're not going to know until the morning that the assignment is due, and hopefully everything works out, but if not, you'll get an email from me saying I can't access your repository, and you've lost 25 points. And if you catch that email and you can get a hold of me and we can fix that in time, right, then that's fine. But if not, you're going to end up with a 0 on PA1. Even if you spend, 80 hours writing the code and you get it all to work perfectly, if I can't get to your repository, you won't get graded for it. And there's absolutely no reason not to do this on day 1, okay, or day 4 in this case. Make a README file, just say hello, do a git init, git add, git commit, git push origin master, and then hop on to GitLab, set me up as a reporter. And here's the thing, if you know how to do that, it'll take you a minute or 2 to do. And then you don't have to worry about it for like 2 weeks. If you don't know how to do it, well, you got to figure it out, right? And you want to figure it out as soon as possible so that you can be using GitLab to save your code and your work and have safety there, and so you don't have to worry about how to submit it Thursday night. So really, I recommend trying to do this today. And shoot me an email and say, hey, I pushed my repo over, can you see it? And I'll let you know yes or no, and if not, we'll figure out what to do. Yeah?
Do you want the repo to be named PA1 or?
Linked list 1, uppercase L, uppercase L. So look at the assignment, it's spec'd out exactly, and the number 1, yeah. We're going to look at PA1 in a few minutes. And it's GitLab, not GitHub, and you got to give me reporter access, not guest access. And me is Nick Macias, not Nick Macias 3. So it's exactly the same as in 224. If you were in 224, you've seen this before. If not, definitely try to do this ahead of time and talk to me, and we'll make sure that it's there and accessible to me. All right, so let's look at ODP 203. Hey, it's right here. So ODP 203 is part of PA1. We're going to look at PA1 next, okay? But ODP 203 is basically this business of where should I put my new node in my linked list array? So let's say we have a linked list that looks like this. So here's a 10, and here's a 20, and here's a 30, and here's a -1. And let's just suppose this is what our array looks like. Okay, remember how we interpret this. Our sentinel node is always index 0. That points to the first node of our list, which is index 3. That's the number 10. Bang, right there. That's followed by the node at index 4. That's a 20. That's that one. That's followed by the node at index 1. That's a 30. That's this node. And the next value there is our flag -1, saying that's the end of the list. So this is an example of an array that corresponds to this linked list. Now there could be a lot of different arrays that correspond to this. It might just be 10, 20, 30, but as you insert and delete and move things around, right, things can get jumbled up. Okay, if we want to insert a new node, what were we doing on the board yesterday? We said, let's move through here and find the first node where valid is equal to 0. and we would say, oh, that's at index 2. Okay? ODP 203 is writing a function that does that for you. You give it an array like this, and it starts from the beginning, and it finds the first node where valid is equal to 0, and it returns the index of that, 2 in this case. So it does that thing that we can do so easily visually, which is just scan down here, find the first 0, index 2. Your getNode function does that in code. Okay, so it's called getNode. It takes an array of struct nodes, and it returns an integer. And it searches for the first node where valid is equal to 0. And if it finds a node where valid is equal to 0, it returns the index of that node. So 2 in this example we were just doing. But it's possible that in your array, every single entry is going to have a 1. Okay? And your array actually contains 100 elements, so it goes down to index element 99. So you want to check all 100 entries for a place where the valid flag is equal to 0. If you find one, return the index. But if you get all the way through all 100 entries and every valid flag is 1, what does that mean? I've got 100 things in my list. I don't have any space left to store a new node. In other words, I'm out of memory. And in that case, you want to return the value -1. And that's another flag saying there's no index available. Okay, so it'll tell the user you're out of memory. So this is really just a for loop, right? Take your array and for I equals 0 to 99, check if element I is valid is equal to 0. If it is, return I. Don't change the valid flag. It doesn't say change the valid flag to 1. Just return the index. Okay. If you get all the way through your for loop and you never returned, you know that all the valid flags were 1. Now you return -1. Does that make sense? All right, so code that up. Write some code in main to initialize your array to, have interesting valid flags like this, including a test where all the valid flags are 1. And for each of those conditions, call your getNode function, print out what it returns. Make sure it either returns the first available index or it returns -1. Once your code's working, go ahead and link it in with the test bed, okay, like this, and then assess it like that. Yes?
How do you determine how many times you go through the check?
100.
100.
Yeah, so in PA1, this is part of PA1, so in PA1, which we're going to look at next, it specifies your array has 100 entries, so 0 through 99. And start looking from element 0, even though 0 is a sentinel node, start looking from element 0.
So we're assuming that the 0 is...
So we're assuming we're going to set the valid flag to 1 in element 0. All right, any other questions on 203? Cool. All right, so let's look at PA1. All right, so programming assignment 1, not surprisingly, is about playing with linked lists. Linked lists implemented as an array of struct nodes. So same struct node definition we've been using for ODPs. 3 integers, data, next, and valid in that order. And data is an integer that's stored in our list. Next is the index of the next node in the list, or -1 if it's the end of the list. And valid is a 1 if this is actually a piece of our list, or 0 if that spot is available to be used. All right, really, really important detail. we've got this magic value -1. We don't want to use -1 in our code. I'm going to require that you use a define in the beginning of your file which defines the word myNull to be equal to -1. And every time you want to check to see if something's equal to -1, I want you to check to see if it's equal to myNull. Every time you want to set something to -1, I want you to set it equal to myNull. So, last node in list. List bracket index dot next equals, don't set it equal to -1, set it equal to myNull. Okay, you will lose points if you code -1 in there. There's a reason. If you're looking to see if this is the last node, don't check to see if it's equal to -1, see if it's equal to myNull. Okay, it's exactly the same thing because in the beginning of your file you're going to define myNull to be a symbol for -1. So as far as the behavior of your program, if you actually just use -1 instead of myNull, your code will work perfectly. Okay, but I'm still going to take off points because I really, really want you to use the word myNull instead of this magic number. The reason being, in PA2 our magic number is going to change. We're going to have to use 0 instead of -1. And if you code -1 throughout your program, you're going to have to find each of those and change them to 0. If you code it up as myNull, then all you're going to have to do is change this one define statement. And in fact, it's already defined for us. And it's going to make your code a lot easier to modify. So use that symbol myNull instead of -1. Okay, your main program should define an array of 100 struct nodes. And I'm going to call it list here. You could call it something else, but list is meaningful. So list is the actual linked list. Okay, it's the actual array of 100 entries. It's this thing right here. Okay, going down through and including element 99. All right, we have to talk about abstract data types. You know what a stack is, right? Either from 270 or from 224. Or not. Raise your hand if you know what a stack is, because actually some people may not have done 270. Stack is just a place where we can store numbers with this interesting property that the last number you store is the first number you retrieve. So if I put onto my stack an eraser and a piece of paper and then a marker, and then I say give me what's available in the stack, the first thing I'll get is the marker, and the next thing will be the piece of paper, and the last thing will be the eraser. And if I put an eraser and a piece of paper and a marker, and I take off the marker and I take off the piece of paper and I put on a marker and I say what's the next thing available, it's going to be the marker. The last thing you put in your stack is the first thing that comes back. Okay, it's just a way of storing information, but it's useful in computer science. And so we implement stacks in C or in assembly language or in hardware, and there's lots of different ways we can implement a stack. But as somebody who wants to use a stack, all we really want to do is say put this on the stack or give me whatever's available from the stack. Right, what we call push and pop. And you can implement a stack with an array. You can implement a stack with a linked list, which we're developing in this course. You can implement a stack with a piece of paper and a pencil. And every time someone wants to push, you can write down the thing that they pushed. And when they want to pop, you can just read the thing that's at the bottom of your list and cross it off and give it to them. But to somebody who's using a stack, all they want to see is push and pop. I want to put something on the stack by saying push. I want to get something from the stack by saying pop. They don't want to have to say, tell me what's at the bottom of your sheet of paper, or tell me what's at the element whose index is given by this variable called SP, and then decrement the stack pointer, or increment the stack pointer, or subtract 2. So there's this like firewall that divides sort of the user code from the implementation. So let's think about a linked list. We want to initialize a linked list. We want to insert things into our list. We want to delete things from our list. We want to search for things in our list. Okay, we were doing some of these operations yesterday. We're going to have a series of functions called init, or add, or delete, or search. And our user code is going to interact with those functions. Our user code is our main program, right? And we're the user, we're the one writing the main program as well as the linked list code itself. But imagine that you're creating a linked list, you're writing a bunch of C code that lets somebody work with a linked list, and then you're giving this code to somebody. And they're writing a main program that adds things to a list, deletes things from a list. You've got code over here which does this implementation. The idea of an abstract data type is that to the user who is working with a linked list, all of their interactions with that linked list come through this set of functions. And those functions will do things like, when I want to initialize the linked list, I'm going to make a loop which goes through here and sets all these valids to 0 and sets this next equal to -1. Okay, that's something the init function will do. I would never want the user in their main program to do those operations. Why? Because next week I might come up with a new way to implement a linked list. I might implement a linked list using dynamic memory. Or I might decide, you know, I want my Sentinel node to be down here at index 99. In which case, this is not the field I should set to -1. This is the field I should set to -1. And if I make that change in my linked list implementation, and the user's main program is manipulating these fields, they have to modify their main program. Okay? So the idea of an abstract data type is we provide the user an interface to our data type, and they just see a linked list as a way to initialize, add, delete, search. But we write the code that says how do we initialize, how do we add, how do we delete, how do we search. Now if we decide our linked list is going to hold 1,000 things instead of 100, yeah, we have to change our for loop in our search and say, or in our init and say, let's initialize 1,000 things instead of 100. But the user, they never wrote a for loop saying set the valid flag equal to 0 for all. They just called init, and their code still works. They might have to just recompile it, right? They don't have to change their code because they initialize it by calling the init function. But as the implementers of this linked list, we change the init function to say let's loop 1,000 times and set valid equal to 0. So we want this really strong division between what a main program will use to interact with our data structure and how we actually implement that. Okay, so keep that in mind as we go through PA1, and we'll see what's on each side of this firewall. These are the implementation details. Okay, these are the things that the user is going to use to interact with our program. But the code for these is going to do all the low-level stuff, the for loops and setting things equal to -1 and checking to see if this is 0 and so on and so forth. Okay, but these are the functions we would give to a user to say, hey, when you want to work with a linked list, here's the things you should call. Okay, so we've got an init routine. Init takes an array of struct nodes, sets the valid flag to 0 for all of them, sets the sentinel's valid to 1, sets the sentinel's next field to my null. That's the code for -1. Okay, that's what your ODP 202 did. So set up the Sentinel node and then make a loop and set up the other 99 nodes to have valid equal to 0. And again, ODP 202 did some other stuff. It set values to 999 and things like that. You don't have to do those. Okay, make the valid flag 0, make the Sentinel valid, make the Sentinel point to my null. That's all you need. All right, there's a function called add. Add takes an array of struct nodes and it takes a single integer and it tries to add that integer to the linked list. So this is what we were doing on the board yesterday. Going through these structures, and if you wanted to add a 25, right, we found the node that came before it, we found the next empty spot, put a 25 there, made it valid, had that point where the prior node pointed, and then had the prior node point to the new node. So we did that several times on the board, and you did that in your homework. This is what the add function does. Okay, and it's all kinds of low-level, gushy manipulations of this array of struct nodes, right? But to the user is just going to say add list comma 25, and boom, it'll update all that stuff. Okay, add actually returns an integer, and that integer is a flag. If it succeeds in adding the number to the list, it returns a 1 saying success. If it does not succeed, it returns a 0. Why would it not succeed? If there's no space left in the array. So first thing when you're adding is you find a spot where you can insert a new node. If there are no spots, if every valid flag is 1, you're out of space. And so add just returns a 0 saying, sorry, there's no memory left. And then whoever's writing the main program, when they say add list comma 25, they're responsible for checking the return value to know whether or not it got added. So they could say if add list comma 25 equals 0, print, sorry, we're out of memory. All right, there's a print function. Print will basically print out the contents of the data field of each node in your linked list. So this is what we can call traversing the list. And if this is the structure corresponding to our linked list and we say print, what should it do? Don't just print 30 something 10 20. Okay? Don't go through your array in order and print things out. Don't go through your array and check the valid flag and print things out. That's not traversing the list. The only way to traverse the list is start from the Sentinel node, see where it points, print that data value. See where that points, print that data value. See where that points, print that data value. And keep doing it until you find that you're pointing to my null. And then you've hit the end of the list, you're done. So start off with index 0, that's pointing to a 3. Print this data value 10, that's pointing to a 4. Print the data value 20, that's pointing to a 1. Print the data value 30, that's pointing to my null, you're done, return. And you've printed 10, 20, 30. All right, and if your list is set up in such a way that it's always sorted, then this print function will print your nodes in sorted order. And print doesn't return anything, so it's declared to be void for its return type. All right, delete removes a node from the linked list. So you give it a linked list array and a number that you want to delete, and it searches for that node, and if it finds it, it deletes it by taking the previous node and having it point past the deleted node, and then clearing the valid flag in that deleted node. And delete does return an integer. It returns 1 if it succeeded in deleting it. It returns 0 if it did not succeed in deleting it. The only reason it will not be able to delete is if it does not find it. So if I try to delete a number that's not in the list, delete should return a 0. And then search takes a linked list array and a number, and it returns an integer saying, I found the number, that's what a return 1 means, or I did not find a number, that's what a 0 means. So to search, we basically do the same code as when we're printing, but instead of printing, we compare each node's data value to what we're searching for. And if we find it, we return a 1. If we get to the end of the list and they haven't returned, we know the number is not in the list. Return is 0. Okay, so those routines, that's the abstract data type view of a linked list. That's the stuff the user uses, the main program uses to interact with the linked list. But implementing those routines will require you to do some more low-level stuff, to search through the array in a for loop. Okay, to look at this thing's next field and use that as an index to get to the next node in your array, and so on and so forth. So here's the implementation of these. Your linked list is an array of struct nodes. Struct nodes have data next and valid. Valid is 0 if it's not valid, 1 if it is. Right? And we could do that differently. We could say valid is 1 if it's valid and -1 if it's not. Right? And as long as we change our code for init and print and search, the user is not going to have to change their code. But if the user is going through and looking for a valid flag that's equal to 0, and we're actually using -1, their code would break, right? So we never want the user to interact with these low-level details. So main program, these are the only functions you want to use from the linked list thing that we're building. But to implement these, we're going to write other functions and write some low-level code. So one function we're going to want is something called getNode. This is ODP 203. GetNode takes an array of struct nodes and it returns an integer. And the integer value is the index of the first node where valid is equal to 0. So if this is my array called list and I say getNode parentheses list, it should return a 2. Okay? It doesn't change that field. It just observes the valid field, and the first one that's a 0, it returns that index. If this happened to be a 1 and I called getNode on list, it would return a 5. If all of these are 1 all the way down through element 99, then getNode should return, guess what? My null. Okay? Don't return -1, return my null. And anytime you want to find a node in your array to use, don't write a for loop, call getNode. Okay? GetNode's going to have a for loop. It's going to go through, it's going to check the valid flag. But in your add function, you want to insert a new node, don't write a for loop that goes through and checks the valid flag in your struct node array. Call getNode. Okay, this is really important. So we want modularization. Okay, getNode looks for an available node. Add calls getNode to find an available node and then puts the new data in that location. Main calls add to add something to the linked list. Okay, so we want this rigid hierarchy. And we don't want main to make a for loop and find a node where valid is equal to 0. Okay. All right, release node is the opposite of getNode in some sense. Remember when we delete a node, if we decide we want to delete the 10, we're going to have to change the sentinel to skip over the 10 and point to the 20, and then we're going to need to change this valid field from a 1 to a 0. Okay, I want you to write a function to do that. That function is called release node. And release node takes your struct node array and an index and sets that element's valid flag to 0. It's a one-line function. It might seem silly to make a separate function for it, but there's a reason. So release node basically says ll bracket number dot valid equals 0. But write it as its own function. And when you delete, instead of saying ll bracket number dot valid equals 0, say release node ll comma number. Okay, this will make perfect sense when we get to PA2. Because PA2, if you do this right, your main program is not really going to have to change much. In fact, you can change it with one command in VI. And then just recompile, and everything will work great. Okay, but you got to make sure that you're using these functions in this hierarchical way. All right, so you got the high-level view of what the linked list implementation is all about. let's look at the main program. So your main program is a bunch of test code that lets you do things with these linked list routines to see if they're working, right, or to demonstrate that they are working. So your main program should initialize an empty linked list. So it's going to declare a struct node list bracket 100, okay, and then it's going to say init parentheses list, and that will do all the setting of the valid flags and the sentinel nodes next. And then it prints a prompt which is just a greater than sign followed by a space, and it waits for the user to type a command. The user types a command, hits enter, and then the program executes that command, comes back, prints another prompt, waits for a new command. Okay, and you have a very limited set of commands. The first command is I for insert. So I can say I space followed by an integer, and this will insert the integer into the list in sorted order. And once this command executes, I get exactly one of three possible output messages: success, node already in list, or out of space. And I want you to stick to this: uppercase, success, node already in list, or out of space. One line of output, and that's it. Go back to a prompt. Okay, success obviously means it succeeded in inserting it. Node already in list means you tried to insert a number that was already in there, so I didn't put it in again. Out of space means there is no space available in the array. Okay, P says, show me the contents of my list. The response to that should be one line of output, which is the set of numbers in order with a single space in between each number. So 10 space 20 space 25 space 30. One line of output, come back to the prompt. S is how you search for a number, so I can say S space 25. If it finds it, it'll say found. If it doesn't find it, it'll say not found. All right, D deletes a number. So I can say D25, and it'll either say success if it deletes it, or if that number's not in the list, it'll say node not found. And then X just exits the program. And it doesn't print any messages, it just exits, and you come back to your Unix prompt. Anything else that you type should print some sort of short synopsis of what the possible legal commands are. Don't print those in the beginning, okay? Just print them if they type in something that you don't understand. Print those out. When you first run the program, all you should do is print a prompt and wait for a command. All right, so let's look at PA1. All right, so I run my program, it prints a prompt. It's just sitting there waiting for me. I can say insert 10, success. Insert 20, success. Insert 30, but I typed something funny after there, so I had an error. So it gave me a help message. Please enter one of the following commands. I misspelled commands. I just lost 20 points. Okay, insert 30, success. So I can say print, there's what my list looks like, 10, 20, 30. I can say insert 15, success. I can say print, now my list is 10, 15, 20, 30. I can say search for 15, it says it's found. I can say search for 16, it says not found. I can delete 15, it says success. I can delete 16, it says node not found. I can type something it doesn't understand, it'll give me a synopsis of legal commands. I can go back to inserting things. I can insert a 15 again and print. I can insert negative numbers. I can insert big positive numbers. And I should be able to insert up to 99 numbers because one of my array's entries is used for the sentinel. And then if I tried to insert one more, it would say out of space. If I try to insert something that's already in there, it'll say node already in list, and it does not insert it a second time. And then when I'm done, I just type an X, and it exits. Okay, I want this very, very clean user experience. No extra output, no variations on the messages, No extra spacing or clearing of the screen or anything, okay? Try to do it exactly like it's specified. The reason being, in addition to making it easier for me to grade, as you move on to other courses, particularly at a university, the program requirements get more and more specific in some cases, and you can get penalized heavily for varying from those. If someone at a university gave you this assignment and you printed a different message, or you didn't print anything when you succeeded in inserting, you would probably lose a bunch of points for that. Okay? Now I will comment on it, and I might take off a few points for PA1, because this is kind of a new level of rigor. But for PA2, I'm going to get even pickier about this, and by the end of the course, I'm going to be like rigid. So we're working up to that. Okay, does this make sense? All right, so deliverables. So your submission should include all of the above routines. Okay, a main program, those functions the main program is going to use, init, add, print, and so on, and then the actual implementation of those functions and any other functions that support it. Your code should be commented thoroughly. Okay, most of this code is going to be non-obvious what's going on. So I expect a lot of good commenting, explaining what's happening. You're going to have a lot of different functions. You want a comment block before each function saying what the function does, what the arguments are, what the return value is, any unusual conditions that should be understood, and so on and so forth. Okay, so lots of commenting. Comment block in the beginning of each file containing your name. Please put your name on your code. The program number, the date, the class, and the synopsis in your own words of what this program or file does. And then a make file for making an executable program. So at the very least, I would like you to have a main program in one file, main.c, and then your linked list implementation, init, add, print, delete, in a separate file, I don't know, linked list.c, something like that. And you can have more files if you want. Okay, I recommend a .h file for a struct node and to define my null, and include that in the beginning of each file. And then a make file that bundles all these things together. And then push it over to GitLab, repo named linked list 1, and make sure I have reporter access.
Is including a .h file just as easy as having a text file that is named .h and then writing in your main account?
Exactly.
Oh,
Yep.
wow.
Yeah.
Okay.
Just include double quote file name instead of angle brackets.
Oh, whoa.
Because angle brackets look for it under typically user include, and double quotes will look for it in your current directory. So, and then if you decide to change what my null is to be -2 instead of -1, you just have to change it in your .h file. And if your make file is written correctly, you can just say make, and it'll recompile everything. And now you're using a -2. All right. Other questions on this? So let's look at deletion as an example of what we need to do here. So suppose this is what our list looks like, and we want to delete the 20. Okay, we know that what we need to do is we need to take the 10 and point to the 30, and then we need to set 20's valid field back to 0. And we can do that visually, right, but we want to be able to tell the computer how to do that. So basically what we need is we need a pair of, I'll call them pointers, but they're really just indexes. We need a pair of things which I'm going to call previous and current. And we're going to move these through the list until current is the node that we want to delete. And when current is pointing right here at the 20, previous should be pointing at the previous node. And now we can say previous next should be equal to current next. And then we'll want to set current valid equal to 0, which we'll do with the release node function. But we've got to get to that spot where we want to delete. And we got to make sure that we have this variable previous that tells us the index of the previous one. So we can do this as a bit of a loop. Set previous equal to 0, because we know where the sentinel node's always sort of sitting before the first node. What would we want to set current equal to?
0.next.
Yeah, so we want to set current equal to, and assuming this is called list bracket 0, or I could say previous dot next. Right? Because the sentinel node's next field, that's the index of the current node. So right now I've set previous to be 0, and in this case I've set current to be index 3. Okay, if list bracket current dot data equals n, so this is delete n. If the current node's data is equal to n, then we want to delete it. Well, the current node's data is equal to 20, that's not where we want to delete. So we're not going to delete the 10 node. What we want to do is move current and previous down. Okay, so we could do the following. Set previous to be equal to current, and then set current equal to list current dot next. Or in this case, list previous dot next. That sets this thing equal to the thing that this is pointing to. Current's going to change to this node. So now this is previous, and current is index 4. And we'll come back up here to the top of our loop. And now we'll say if list current data equals n. Well, list current data is equal to 20. That's the node we want to delete. So how do we delete it? Well, we want the previous node to point where the current node is pointing. So this is what we did yesterday. List bracket previous dot next equals list bracket current dot next. And if that happens to be the last node in the list, next will be my null. That'll change previous next to be my null. So that'll be the end of the list. Otherwise, in this case, it would change that to point to 30. And then we need to release this node. So we could say list bracket current dot valid equals 0, but in fact we're going to say release node. List comma current. And that's just a one-line function that says list bracket current dot valid equals 0. And then we can return. So that's your delete function. One danger here, though, is what happens if our number is not in the list. We're going to keep doing this loop, and we're going to keep moving previous and current, and if we're trying to delete a number that's not in the list, at some point, current's going to become -1, and when we try to index list bracket -1, we're probably going to segfault.
Since we're abstracting it, can we just ignore that and search before we delete?
Yes, so this is exactly what you want to do, is before you delete, call search. In your main program, if the person says delete n, call search n first. And if you don't find it, return return an error saying it's not in there. Or in your delete function, you could call search, right? And if it doesn't find n, just return a 0 saying I can't delete that, it's not in the list. Right? So up here in the beginning, search for n. Do it here, not in your main program. If search comes back with a 1, you know it's in your list. Now you can safely iterate here, and you know that eventually you're going to find a spot where list current data is equal to n, and you can delete it and return. I guess it would be a return 1, because delete returns a value. But before you do that, search. If you don't find it, return a 0. All right, insert's the same way, but we'll talk more about this tomorrow. But if you want to start working on this, start off with an insert function that just inserts at the beginning. Forget about keeping it sorted. We'll spec out pseudocode for that tomorrow. All right, so we'll talk more about steps to move forward with this tomorrow.